All right, good evening. I'm Professor Sean Tavallia, founding member of the board of Hamptons Observatory and academic chair of physical sciences at Suffolk County Community College. On behalf of my fellow board members and colleagues at Suffolk Community College, I'd like to welcome everyone to tonight's presentation. For those of you who are unfamiliar with our organization, the Hamptons Observatory was founded over 20 years ago with a mission to provide free, year-round, family-friendly educational events that focus on science and the natural world. After the presentation, please visit the Hamptons Observatory website to learn about future presentations, join our email list, or donate to help ensure that we can continue providing these incredible opportunities. If you feel inspired by tonight's presentation, please visit Suffolk County Community College, where you can begin your journey into a scientific career at one of our three campuses in Brentwood, Selden, or Riverhead, New York, or from the comfort of your own home through our online offerings. As we begin tonight's presentation, I ask that you keep your microphones muted, but please feel free to post questions in the chat. At the conclusion of the presentation, we'll do our best to address all questions. Tonight's speaker is acting Principal Investigator for the Pixel instrument, which is one of 7 instruments on board the Mars 2020 Perseverance Rover. He's worked extensively on NASA Mars missions, playing roles ranging from scientist to rover instrument design and operations specialist to science and engineering operations team leader. In 2006, he received a PhD in geosciences from Stony Brook University. From 2006 to 2007, he was Caltech postdoc scholar at NASA's Jet Propulsion Laboratory, where from 2007 to 2013, he served as a research scientist. In 2013, he joined the faculty of the Department of Geosciences at Stony Brook University, where he is currently assistant professor. His research is focused on the study of the properties of ancient sedimentary rocks on Mars and Earth and what they reveal about past environments, habitability, and biology. Please join me in welcoming my friend and colleague, Joel Hurowitz. Joel, it's all yours.
Awesome. Thank you so much, Sean, and thanks very much for the invitation to come speak to the Hamptons Observatory and Suffolk County Community College. So I will go ahead and jump right in. So the subject of today's or tonight's talk will be the discovery of a potential biosignature in Jezero Crater on Mars, and I'll describe what a potential biosignature is in just a couple of minutes. So I figured let me make sure this works. Start with a brief introduction to Mars just to get everybody on the same page, although I assume with this audience I won't have to do too much of that. Um, but anyway, I'll give you just a little rundown of our neighbor planet. So when we look at Mars, it is a little further away from the sun than the Earth. It is the fourth planet in the solar system. And Mars is a considerably smaller planet than the Earth. Its radius is roughly half that of the Earth, and it's about a third of the size. But its structure is similar to that of the Earth. The interior has a crust. It has a mantle and it has a metallic core, all of which are quite similar to what we see on the Earth. And that sort of geological similarity has given rise to similar geological activity at the surface of the planet. Uh, Today, the Martian environment is a fairly cold and inhospitable place with a very thin atmosphere covering its surface. You can see a sort of beautiful image here taken from orbit of Mars at a kind of oblique angle where you can see this sort of thin atmosphere that's very dusty, sort of hovering above the planet. Because it has such a thin atmosphere, Mars experiences some very significant temperature variations from day, from day to night, and over the course of the seasons. At the poles, Mars is about minus 185 degrees Fahrenheit, which, by comparison to the Earth, a typical day on the Earth's south pole is around minus 55 degrees. Summertime temperatures at the equator on Mars can get as warm as 50 degrees Fahrenheit. The atmosphere on Mars is very thin. It's about 100th of the total pressure of the Earth's atmosphere, and it's nearly all carbon dioxide. There's almost no oxygen or nitrogen in it. And Mars is also very dry. There's no liquid water at its surface today, as far as we can tell. It does have polar ice caps, though. Mars is also a planet of topographic extremes. You're looking here at two sides of Mars where the topography of the planet has been rendered in color. So high points on Mars are in white and red, and the low points on Mars are rendered in blue in this sort of false color imagery here, or false color data set. There is almost 100,000 feet of relief between Mars's highest point on the volcano Olympus Mons and its deepest point, this large impact basin called Hellas Planitia. That 100,000 feet of relief compares, if you compare the sort of high point on the Earth, Mount Everest, which is maybe approaching 30,000 feet, down to the sort of deepest depths of the ocean trenches and other sort of I don't know, call it another a few miles is the extremes of topography are significantly greater on Mars than they are on the Earth. Part of that topographic extreme comes from the presence of this big volcanic complex that includes Olympus Mons, Ascraeus Mons, Pavonis Mons, and Arcea Mons. These are the tallest volcanoes in the solar system. Olympus Mons on its own is 85,000 feet high and 375 miles across at its base. If you were to pick Olympus Mons up and put it on the Earth, it would cover the entire state of Arizona. So these are really, really big volcanoes. The thing that really attracts us to Mars as a target of exploration isn't so much those topographic extremes, but the fact that when we look down at the surface of Mars, we are often presented with images like you see here, where we see that there are river networks that look like they are cut into those topographic extremes on the surface of Mars. And these river networks tell us that at one time in Mars's geological past, water was falling on its surface in the form of rain or maybe in the form of snow melt. It was draining across the surface and carving rivers into the surface of the planet. And if we follow those rivers down into basins where the river water would have been deposited, what we oftentimes find are spectacular deposits of layered sedimentary rock, where water was carrying sediment and delivering that sediment sort of layer by layer by layer into basins where the water was collecting. And if you want to understand something about how the environment on a planet is changing through time, then these layers of sedimentary rock are the perfect place to go prospecting because each one of them preserves a snapshot in time of the environment that those sediments were being deposited in. So these are oftentimes the targets of our exploration are places on Mars where sediments like these have accumulated. Over time, we've kind of built up a picture, a sort of understanding of the changes that Mars has gone through over its geological history. And it leads us to sort of imagine that Mars at one time looked like the planet that you see over here on the left side of your screen, a watery planet with a thicker atmosphere and clouds sort of moving across the surface that has over time transitioned to the planet that you see over here on the right, this cold, dry, desiccated planet that we see today. And we know that the time at which Mars was kind of in this rather Earth-like state that you see over here on the left was a long time ago in the planet's geological history. We can date the surfaces of the planet using techniques like crater counting to tell us that if Mars was ever like the planet you see over here on the left, it was probably like that 3.5 to 4.5 billion years ago. There's a number of lines of evidence, and I won't spend too much time on this particular slide here, but this slide kind of makes the point that when we look at Mars's geological history from its most ancient time, 4.5 billion years ago here on the left, through to its present time here at time zero, which is today, a number of changes have occurred at the Martian surface to take it from a more Earth-like planet to a planet that is not particularly Earth-like anymore. And what we see is that the period of time in Martian geological history when there was a lot of volcanism taking place, when Mars had an active magnetic field, when rivers and lakes and big catastrophic outflow channels were moving around at the surface of the planet, that was all happening in the ancient part of the Martian geological record, 2.5, 3.5, 4.5 billion years ago. And then over time, it has transitioned to what we see today. And we've actually developed a pretty good idea for what has caused this change. What happened to Mars, we think, is that early in its geologic history, it stopped being volcanically active. It kind of started to cool down, probably because it's smaller and lost a lot of its internal heat earlier, and its magnetic field shut down. And once that magnetic field shut down, it no longer had a protective envelope around its atmosphere to prevent the solar wind coming from the sun from stripping its atmosphere away to space. So over time, that solar wind has been stripping the Martian atmosphere away from the planet at about a quarter-pound rate every sentence or every second. And as this quote here from a scientist named Bruce Strakowski says, this is sort of like the theft of a few coins from a cash register every day. That loss becomes more and more significant over time. And so Mars has basically sort of lost its atmosphere, lost its surface water because its atmosphere has been stripped away to space. And that's really why the planet looks the way it does today. But again, when we look back at Mars in its ancient past, we do think that this was a planet that was probably more Earth-like in its character. It had abundant liquid water, it had a thick atmosphere, and so it's sort of natural for us to ask the question, if Mars had abundant liquid water and a thick atmosphere at its surface, and those environments were sort of habitable to life as we understand it here on the Earth, did Mars ever have life? Did life originate there? Was it present at its surface? And how can we go looking for what kind of life may have been on Mars if it was there? So what we need to do in order to sort of address that question is take a look sort of through the lens that we have by understanding the evolution of life on Earth. That's really the only example we have to compare to. And so what I'm going to do is I'm going to take a look at this next image to try to give a sense for what kind of life may have been present on Mars if it was ever there. Okay, so here what you're looking at is a timeline of the biological events that have occurred in the history of the Earth. So the timeline is kind of laid out here from the beginning on the left, 4.5 to 5 billion years ago when the sun first ignited and the Earth first formed, all the way through to the present day over on the right-hand side. Actually, it doesn't quite get as far as the present day, but it gets close. What we know from studying fossils on Earth is that the biological record of the Earth, from when we can first start to read it about 4 billion years ago through to around 500 million years ago, almost all life on Earth is single-celled microorganisms. There's nothing that we would recognize as a sort of familiar fossil in the earliest part of the Earth's biological record. We don't start to see things like corals or lizards or fish or dinosaurs until we get to about 500 million years ago. So if we're looking for signs of life on Mars, and Mars was at its most Earth-like state maybe 3.5 to 4 billion years ago, really what we're looking for are the kinds of signals that single-celled microorganisms would leave behind in the Earth's in the rock record. So maybe to make the point a little more plainly, uh, we're not looking for the kinds of classic fossils that you might associate with fossil prospecting on the Earth. We're not looking for fish. We're not looking for bones. What we're looking for are things like you see over here in the right-hand image, which are microbial fossils that get left behind in the rocks when microbes are near the Earth's surface. They're forming little communities, and those communities are then getting buried and preserved and leaving behind these sort of unusual layers in the rocks that we can see. So This is an example over here on the left of sort of classic fossils. Everything there would be, less than around 650 to 550 million years old. Microbial fossils can be found in the Earth's geological record up to, rocks as old as 3.6 billion years old. And maybe one other important little sort of nuance here is that when we're looking for fossils of microbial life, there's sort of two types of fossils that we can go looking for. There are fossils of things that were living in the sun and were performing photosynthesis, like these microbial mats that are currently growing in a lake, or you can find these in just about any surface water body on the earth. When those things die and get fossilized, they leave behind layers of microbial mats in the rocks, like the ones you see over here on the right. There's also another biosphere that is completely non-photosynthetic and kind of lives in the dark below the ocean's surface or below the subsurface. And those types of microbial communities leave behind much sort of subtler clues to their existence, but we know what to look for when we're looking for them. Here, what you can see is an image of deep ocean sediment that is 2 to 3 kilometers below the ocean's surface. And if you dig just a few meters below that sediment water interface, what you'll find are things like these little mineral aggregates that get left behind by microbes that are metabolizing in the sediment and changing the properties of the sediment that they're living in and leaving behind these little telltale markers of their existence. So keep these two things in mind as we move forward. Okay, so we have gone to Mars with a rover named the Perseverance Rover that is equipped with an amazing scientific payload that we designed in order to study the geology of our landing site so that we could understand what kind of environment that landing site was formed in. Maybe it was formed in a lake or a river or something else, whether or not that environment was capable of supporting life as we know it, and ultimately whether the signs of a former biosphere are preserved in those rocks. And once we find rocks that are interesting enough to us, what we can then do is collect samples of those rocks and store them on board the rover so that they can eventually be brought back to Earth by another mission that I'll show you at the end of the presentation here. One of the instruments that is sort of near and dear to my heart, because I'm the acting principal investigator for it, is named Pixel. Pixel is sitting out here on the end of the rover's arm, and Pixel is a chemical analyzer that provides us with information about what chemicals are in the rocks that we're investigating and where those chemicals are located and what minerals they're located in. And that kind of textural information is really important for us to be able to identify things like these chemical biosignatures or microbial mat fossils that we see in the terrestrial rock record. So here I'm just going to show you really quickly an animation of Pixel approaching a rock in the laboratory and scanning its X-ray beam across the surface of the rock. And what it does as it's operating is it collects images of the rock surface, like the one you see over here on the right. And then with its X-ray beam, it analyzes the surface of the rock and identifies what chemicals are present in the rock and what minerals they're associated with. So it produces results like the ones you see in this sort of middle panel here, where I've rendered chemistry in false color. You can see an RGB map where the abundance of iron is shown in red, the abundance of magnesium is shown in green, and the abundance of silicon is shown in blue. And by mixing those components together, we can see where things like a mineral called olivine are located, where a more silica-rich mineral like this one called pyroxene are located, and we can sort of work out how this rock formed using that chemical information. And we'll come back to that again in just another few minutes. So really quickly, before I jump into the results from Jezero Crater, I just want to set the stage by describing to folks what it is that we mean when we talk about potential biosignatures. And there's a well sort of understood definition within the astrobiology community that says that a potential biosignature is basically a feature in a rock that is consistent with biological processes, and that when we encounter it, challenges us to attribute it to inanimate or biological processes, compelling us to gather more data before we can reach a conclusion as to the presence or absence of life. Okay, so what that means is when we see features in rocks that might have been formed by biology, we can call those potential biosignatures, but we don't always have enough data to conclusively say, yes, it was biological or no, it was not biological. So we need more data in order to reach that determination. And the other bit of text here at the bottom, there's a lot of text on this slide. The point here of this lower set of text is just to say our confidence in understanding whether something is a potential biosignature or not is improved or increased when we understand the nature of the rocks that those biosignatures are found in, and whether those rocks preserve evidence of an environment that life could have lived in. Okay, so that kind of sets the stage for where we're going here. Table, I'm going to skip this other than to say that there are a number of different classes of potential biosignatures. And what I'm going to show you incorporates elements of 4 of those classes of potential biosignature, which is really exciting. Okay, so let's go to Jezero Crater. So where are we on Mars? So so you can see over here, there's this, again, this globe of Mars rendered in false color. And what you can see is that there's this big meteorite impact basin called Isidis Basin, which is about 3.9 billion years old. And on the rim of Isidis is another impact crater called Jezero Crater. Jezero Crater is an impact crater formed by a meteor striking the planet Mars that is about 50 kilometers in diameter. So it's about the size of Lake Tahoe. And what excited us about that particular crater is that when we looked at it from orbit, what we saw coming into the crater was a channel that looked like a river valley. And at the end of that channel is this big deposit that kind of makes a fan shape. And that deposit is the characteristic feature of water flowing into a standing body of water, a lake, and depositing its sediment as that flowing water decelerates when it hits the lake, and it makes a delta. So imagine the Mississippi River Delta. That's the Mississippi River carries sediment to the Gulf of Mexico. The river slows down, it deposits its sediment, it makes the Mississippi River Delta. This is exactly the same thing, except it's on Mars. So if we want to go looking for signs of life on a planet, you could do a lot worse than to go to a crater that once had a lake in it that was depositing sediment in a delta. So what you can see here is this is a portion of that crater. The white line shows the rover's traverse from where we landed out on the crater floor here, all the way through some of our investigation of this delta, across a unit that we called the margin unit, and into the river channel called Neretva Vallis that was carrying sediment from the river to this delta. We have since actually left the crater. We're actually out here on the rim of the crater exploring the rocks that are outside of Jezero Crater. We completed our investigation in Jezero sort of towards the end of 2025. This white box shows you a zoom up where I'm going to zoom into to show you these rocks that were so exciting to us that we encountered within the Neretva Vallis River channel. So here again, what you're looking at in the white line is the path of the rover's traverse into Neretva Vallis, up Neretva Vallis, across the northern side of the channel, and then down to the southern side of the channel. And these little yellow triangles show you the locations where the rover parked and deployed all the instruments out on the end of its arm to investigate these sort of light-colored sediments that you can see lining the channel in one area that we called the Bright Angel outcrop, and over on the southern side in this area called the Masonic Temple outcrop. Now, from the ground, these rocks look really exciting to us. I'm going to show you a picture taken by the rover from the location of this place called Walhalla Glades. So here, that's what we're seeing in the next image. And what you're looking at in this upper mosaic is a 360-degree mosaic looking from the position of Walhalla Glades down here, looking north towards the northern wall of the river channel, straight in front of us, and down to the right is the outflow of the channel towards the delta, and up here on the left is leading back up the river channel outside of Jezero Crater. And what we saw when we looked at these images from inside of the channel was that it was filled with sediment, this kind of light colored, sort of vaguely layered looking sediment that was sort of lining the river channel. And we've actually, on board the rover, we have an instrument called a ground penetrating radar. Its name is RIMFAX. And that ground penetrating radar can send radar beams into the subsurface. They get bounced back, and that tells us about the structure of the rocks underneath the rover, beneath the surface of the planet. And that's what you're seeing here down on the lower left is the radargrams collected by RIMFAX from within the river channel. And what you can see perhaps is that it has a sort of curved shape, just like you'd expect for a river channel that was getting lined with layers of sedimentary rock. Okay, so all of that allowed us to determine that the sediments of the what we call ended up calling the Bright Angel Formation are not found outside of Neret Vallis. They're only found inside of this river channel, and they are basically lining the river channel. We collected a whole bunch of observations that allowed us to put together sort of a depositional model for how this river channel got lined with sediment. And this is what that model looks like. It kind of goes from upper left across to the right, down to the bottom left, and across to the right again. So you're sort of looking at the river through time here. And our basic thought is that what happened is that this river channel was being carved away by a moving river. And at some point in the history of this river, the bottom of the river was dammed, maybe by a landslide, maybe by an impact crater, maybe by ice. We're not really sure what caused it, but it created a dam that caused the river to back up behind that dam and fill the channel of the river up with a lake that was there temporarily. And inside of that lake, the sediments, here you can see in sort of yellow and green layers, were deposited inside of that river channel, lining it. And then eventually the dam was breached. The river went back to its normal drainage and started carving its way back into the sediments that were deposited here when it was a lake. So that's where we think all of these sediments in the river channel came from. When we look at these sediments, what we see is that the sediments of this Bright Angel Formation are really sort of different in their color properties from one place to the next, which is actually really kind of interesting. Um, we see when we look at some locations, like this one over here at Masonic Temple, the rocks are really sort of rusty red in character. Sometimes, like in Walhalla Glades, they're a little bit closer to sort of tan in color. And in some places, like we see up here on the north wall of the channel, they're really almost bright white in color. And so we wanted to understand what could cause the color properties of these rocks to change so dramatically. So what we think happened here is that these sediments probably started their life out looking kind of like the image you see over here on the left. And the model we have in our mind is that somewhere outside of the crater, there were rocks that were being weathered and chemically oxidized by rainfall and by weathering reactions that make soil. And those products of weathering that we see up here on the upper left were eroded and carried by the river down into the river channel itself, where they were deposited as really iron-rich red-colored mud. But the question we've been asking ourselves here is, why are some of these rocks really rusty red colored, while others aren't really all that red at all? And in order to answer that question, what we needed to do was to look up close at some of the rocks that were present in the Bright Angel Formation, where we saw some really kind of unique features that may explain the rock color changes that we're observing. So what I'm going to do is I'm going to zoom up here to one of the locations where we performed some investigation at this place called where this target named Chayava Falls is located. Okay, so zoom in one more time. This is what that outcrop looks like from the perspective of the rover. Again, you can see these sort of light colored, layered sedimentary rocks that are kind of in blocks, and they've been sort of displaced and moved around a little bit inside of the channel. I'm going to zoom up one more time here, where you can see some of the places where the rover performed its scientific investigation. Okay, so on the rock, you've got this sort of hole in the rock here that we call an abrasion patch. This is where we take the tool on the end of the rover and we sort of burr our way into the rock surface to remove the surface weathering rind from it. And then we flip over to another tool that the rover has called the GDIRT. It's the gas dust removal tool. And that blows a puff of compressed nitrogen gas to clear those cuttings away and give us a nice clean surface to work on. So we did that here at this target called Apollo Temple, another one called Steamboat Mountain. But the one that I'm going to show you that we're kind of interested in actually isn't here anymore. So there was a target on this rock called Chayava Falls that we analyzed and investigated, and we were so excited by it that we decided to collect a sample there. And so the hole in this rock is where the core that we collected from the rock was extracted after we had finished our investigation there. So that core is named Sapphire Canyon, but the surface of the rock is named Chayava Falls. So when we look at Chayava Falls, here's what we see. This is a rock that is made up of layers. Some of those layers are sort of bright white in color and they've got big mineral grains in them. But in between those layers are layers of sort of rusty red colored mud that looks like it is undergoing some chemical reactions that have changed its color properties. And if you've seen press releases about this rock, sort of as we were discovering it, you may have heard these things described as poppy seeds and leopard spots. So if you look over here on the right-hand side, this is a blow up of what you're looking at in the left-hand image. These little sort of dark colored speckles, those are the things that we call poppy seeds. They're more properly called nodules by geologists. And the things that are sort of larger, these are the things that we call leopard spots, which in geology speak is a reaction front. What's maybe interesting here to point out is that in the process of making these leopard spots, what you can see is that the rock's color properties changed from the sort of rusty red color to a sort of bleached white interior that is rimmed by something that looks sort of dark green to maybe black in color. So what are these things made of? What's going on to cause these color property changes? So I'm going to show you one more view of this same surface. I'll toggle back and forth here just a couple of times. What you're looking at is a map collected by the Pixel instrument of the chemistry of this rock. And here what I've done is to render the chemistry of the rock in the colors red, green, and blue, where red corresponds to iron, green corresponds to sulfur, and blue corresponds to phosphorus. So when you look at these color mixtures, what you see is that the mud is red in color. It's just got a lot of iron in it. The rims around those leopard spots, I'll flip back and forth here again, are kind of purple colored. Purple happens when you mix iron and phosphorus together. So there's an iron and phosphorus bearing mineral there. And inside of the leopard spots, where things are kind of bleached, you get this kind of dull yellow color. That tells you that iron and sulfur are mixing together. And that tells us there's probably an iron and sulfur bearing mineral inside of these leopard spots. The poppy seeds, those are just purple. So they're just iron and phosphorus together. On the next three slides, I'm going to show you some chemical data, and I promise you these will be the only sort of like hardcore geochemistry plots that you'll see, but I just want to show them to kind of point out that we can use this chemical information to tell us what minerals are present in these light colored areas and in these purple colored areas. So for the purple colored areas, when we look at a map when we look at all the data that was collected by the pixel instrument and look at the calcium, phosphorus, and iron content of the rock, what we see is that all those sort of purple colored areas in the previous map, they are all pointing in the direction of a location on this particular diagram that has both iron and phosphorus in it. And it's most consistent with a mineral phase called vivianite, which is an iron and phosphorus bearing mineral phase, like you see over here on the right, that is oftentimes very green to black to sometimes blue in color. So the chemistry is right and the color is right to tell us that this is the mineral that's there. Inside of the leopard spot cores, what we see is that when we look at that same diagram, except now we're looking at calcium, iron, and sulfur, the points from inside of those leopard spot cores are scattering in the direction of iron and sulfur bearing minerals like pyrite, what you might know as fool's gold, or greigite, or pyrrhotite. So these are iron and sulfur bearing minerals, like the one you see over here on the right. This is an image of greigite from the Earth. Okay. There's one other piece of the puzzle here to tell us why it is that these minerals were forming in this rusty red mud. And that is that one of the other instruments on board the rover, called Sherlock, had a look at the mud in this Chayaba Falls target. And Sherlock is our organic chemical sensor. And when it looked at this mud, what it saw in the spectra that it collects was something that we call a G band. It's an excitation in these spectra that is only caused when organic matter is present in the mud. And you can see some of the spectra here from a variety of the targets in the Bright Angel Formation that tell us that this G band is present in all of the mud in this area, or I should say most of the mud in this area. And that G band is telling us that there's organic matter in these rocks. Okay. So when we sort of piece together the full picture and kind of bring it back to what is causing these color property changes in the rock, what we came to recognize is that in the rocks that were really red, like the one over here on the left, they were really organic matter poor. They had no organic matter in them, and they had none of that iron phosphate or iron sulfide mineral, the vivianite or greigite. On the other extreme side, the rocks that are not red at all, they're basically white, have lots and lots of organic matter, lots and lots of vivianite, and lots of greigite. And then rocks like Walhalla Glades are somewhere in the middle. And so what that told us is that there was some chemical reaction taking place between the organic matter in the mud and the mud itself that was changing its color properties and causing the vivianite and the greigite to precipitate, making those poppy seeds and leopard spots. What's really kind of cool is that when we bring this back to thinking about what could cause these changes in rock color properties and mineralogy, if we were to simply take rusty red water with lots of iron oxide particles in it and incubate it in the presence of organic matter and microbes, what we would find is that the properties of that water would change within matters of hours to days to, and sometimes, maybe weeks to months over here on the right-hand side as a result of the microbes in this fluid eating the organic matter and changing the chemical properties of the iron that is dissolved in this water, turning it from a sort of reddish colored solution to a sort of greenish colored solution over here on the right. It's exactly the kind of thing we'd expect to see microbes doing, and exactly the kind of thing that we'd expect them to do in terms of changing the color properties of the rock. But I will say that there are ways to make these reactions go forward in the absence of biology. And so that leaves us at this point where what we think we've identified is a potential biosignature. So I'd show you this image up here on the upper right. This is the same image that I showed you a little bit earlier in the slideshow. What those are clusters of vivianite and greigite, just like we saw in the Bright Angel Formation, But here, where they are, is in sediments that are found off the coast of Taiwan, where microbes have been consuming the sediment and the organic matter and making these little nodules that are the same size as the poppy seeds we see in the Bright Angel Formation on Mars. So it's a telltale clue. It tells us that the things we've seen in the Bright Angel Formation are at least consistent with biological activity in that sediment at the time it was being deposited 3.5 to 4.5 billion years ago. These reactions are commonly associated with biological activity, but some of those reactions that we observe taking place in the Bright Angel Formation can occur via abiotic processes. Doesn't require life, but it could involve life. So, in order to resolve this question of whether or not the things that we've seen in the Bright Angel Formation were formed by life, we need to take another step. We need more data in order to answer that question. And really, the only way for us to answer that question is to take this Sapphire Canyon core sample that we collected from the Bright Angel Formation and bring it back home to Earth. Okay. The instruments on board the rover have basically done everything they can to try to make that determination. Getting any further along the lines of answering this question is going to require the kind of analyses that we can only conduct in a laboratory here on Earth. The kind of cool thing about these features that we saw in these rocks is that if they are biological in origin, then sort of thinking back to earlier in the slideshow, what these are evidence of a non-photosynthetic biosphere. These are not microbial mats living in the sun. These were things that were living in the sediment. And this would actually be totally consistent with hypotheses for the way that the earliest forms of life on Earth would have metabolized and made a living keeping themselves alive, because it's thought that photosynthesis is a sort of later evolutionary invention, and it would have taken some time for that to make its mark on the rock record. Okay, so I'll close here just by showing a really cool sort of animation of the process by which we hope to be able to bring these samples back to Earth and get them off of the Perseverance rover. So I'm going to transition here to this animation real quick. Let's make sure this starts. Okay, here we go. Okay, so that would be the series of missions that we would hope Mars. Oops, sorry. Let me. I'll stop the video there. We would hope would enable Mars sample return to take place. I'll kind of give you just in closing here a little bit of a snapshot of the current state of play with respect to Mars sample return. So it's a complex multi-mission program. So it would require a lander and an orbiter to get those samples back. And late in 2024, the Mars sample return program was put into sort of a reformulation stage to try to understand how to overcome some of the technical challenges that the mission was facing in executing all three of those mission elements successfully. And unfortunately, that went on for long enough that in the uh, fiscal year 2026 Mars sample return or NASA budget, Mars sample return was actually zeroed out. It was terminated. However, uh, in the subsequent year, in the 2026 NASA Authorization Act, the Senate subcommittee in charge of NASA funding authorization uh, it essentially directed NASA to terminate its existing Mars sample return program and then reformulate it in order to try to sort of redesign the Mars sample return mission in a way that would bring the cost and technical challenges associated with this mission, sort of rein those things in a little bit. So all of this is to say that at the moment, Mars sample return is playing a little bit of Pong as we try to figure out whether or not this mission is going to go forward. But I guess I would say that, one of the sort of things that drives us in our exploration of the solar system is to try to answer this sort of fundamental question of whether or not life has ever existed on a planet other than the Earth. And I think that we've got enough evidence in that Sapphire Canyon core sample that we may be able to answer that question if we are able to bring that sample back home to Earth. So with that, I will close out and just say thanks very much for your attention and your time, and I'll be happy to take any questions you might have.
It's great, Joel. Thank you so much.
Of course.
Yeah, we have a few questions. I'll be honest with you, it was hard this time around. We don't often have another geologist in this program. So when I'm looking at the chat, I was really struggling not to answer questions.
Okay.
So I'm leaving them to you.
Oh,
Um,
do you want me to bring up the chat or do you want
no,
do
I could
you
go right for it. It's make it easy for you. So the first question we have is about the mantle and wondering if any parts of the mantle is molten on Mars.
hmm, there is I, I would so I'll sort of start by saying that that particular part of Mars's geology is not really my area of expertise, but I we certainly know from meteorites that we actually have here on Earth that were smacked off of the surface of Mars and eventually sort of landed on the Earth, that volcanic activity has occurred on Mars sometime at least in the last 100 million years or so. So there's every reason to believe that Mars isn't completely dormant, and there may be portions of the Martian mantle that are still molten and capable of producing volcanic eruptions, but we haven't seen any in the time that we've been observing the planet.
Hmm. Along the same lines, Dan Fox wants to know if you have any ideas of why the volcanoes are so much more powerful, and I'm assuming he means much larger than on Earth.
Yeah, it's because Mars doesn't have plate tectonics. So Mars is basically over its mantle, it has a crust, but that crust is completely fixed in place, unlike the Earth, where the plates are constantly moving around. And so the thought, hopefully you can see, I'm sort of doing this with my hands here, is that because Mars is sort of crust is fixed in place, somewhere in the Martian mantle, there was what we call a hot spot that was producing magma and sending it up towards the surface of the planet in much the same way that the volcanoes in Hawaii are built. But unlike in Hawaii, where the volcanoes build up for a period of time, but the plate moves, and so the volcanoes can't ever get that big. On Mars, the plate is just sitting there. And so lava is just pouring out, pouring out, pouring out, pouring out, and just building up these volcanoes in one spot for the entire time they're active.
Excellent. Barbara W. wants to know why did Mars lose its magnetic field?
For reasons we don't actually understand all that well. Magnetic fields require a liquid core that is actively moving. So you have metal that is basically moving and generating an electrical and magnetic current. Probably Mars just kind of got cold enough that the motions in its core just sort of slowed down to a stop. And once that happened, the magnetic field shut down, and that was the end.
Right. And then the weird part is the magnetic field that only exists in one hemisphere.
Yeah, that's right.
Right.
Yeah, as far as we can tell, yeah, the only sort of magnetized rocks are in that southern hemisphere.
And this is a great question. This is from Russ as a Freemason. Curious about naming of the Masonic temple.
Yeah, I think
And,
so.
and while you're doing that, the next question in that was who names the geographic features anyway?
Yep. So before we landed, we divided the sort of the region of Mars up where we knew we were going to be landing and exploring into quadrangles. So sort of just like we would do on Earth, we make these little map quadrangles, and that becomes an area where we do our geologic mapping. Each one of the quadrangles in Jezero Crater is named after a national park from around the world. And I believe that the one we were working in Neuretva Vallis was it's from Grand Canyon National Park. So there within Grand Canyon National Park, there must be uh, a geographic locality named Masonic Temple and a geographic locality named Bright Angel. So basically, once we have that quad, we have a list of names that we can just pick from as we're sort of moving our way through the exploration, and that's how the names get picked.
I was wondering if there was a connection with the Bright Angel Shale, right? That's
Yeah, I think
the
there is.
canyon.
Yep.
Yeah. Uh, so there's a couple questions from Russ too, about any partnerships with private space firms in terms of some of the funding and return missions back.
Yeah, I think that is going to be a big part of the conversation moving forward. I mean, certainly, the big commercial space companies like SpaceX and Blue Origin are very interested in being, launch providers for a lot of these solar system missions. Whether or not there's interest for them in getting involved in the sort of more the parts of the mission that have to do with landing on the surface of Mars, getting things off of the surface of Mars. I think is I guess I want to say it's to be determined, but I certainly know at least SpaceX is very interested in how to get like heavy lift payloads down to the surface of Mars that can support human exploration and get those back off of the surface. So certainly there's a lot of really cool technical challenges there for those companies to help try and solve.
Yeah. And that actually answered the next question was if there was any chance of Elon Musk getting involved, but there it is.
Perhaps it's probably those conversations are happening at
Yeah.
a level way above my head.
And then we have a good question from Mo. Mo's going to be heading your way in the fall, so he's an
Oh,
SEC
great.
student here. What have you learned from Mars so far that you think changes how we should design life detection strategies for de very different worlds, like icy moons or exoplanets, where we will never get such detailed ground truth?
Yeah, that's a great question. I guess I can sort of take it from one perspective, which is that, going in, I think when we were thinking about like what would we look for if we were looking for a biosignature on Mars, I think we probably would have at least my mental image was we'll be looking for those photosynthetic microbial mats that were fossilized and left behind as things that we call stromatolites on Earth. I guess I hadn't really thought that we should be looking that we'd have a better chance of seeing like subsurface biosignatures, like the ones that we see in the Bright Angel Formation. But when you think, I could imagine, maybe you're thinking about like Europa and how might we go looking for signs of life on a planet like or on a moon like Europa, where we're never going to well, I don't say never, but we're not planning anytime soon to put a rover down and send a submarine into the ocean under the Europa ice shell, at least as far as I know. So I think really what we probably need to be looking for are the products of the metabolisms of microbes. So if they produce gases of a certain composition, maybe those are the kinds of things we need to be looking for in our search for life, you know, beyond Mars, I guess. I don't know if that answers the question very well, but that's
You
about the
know,
best I can do.
by really focusing on atmospheric signatures at some point, right?
That I think, yeah, I think as long as we're sort of, in a world where we're sending satellites and not landers and
Uh,
rovers, it's atmospheric biosignatures that are probably the thing we need to look for.
another question just on the Elon Musk note. What do you think about naming rights? Would naming rights on features get you the money that you need?
Oh, like should we name something Mount Elon or something
Yeah,
like
right, yeah.
that?
Let's not give them ideas, right?
No, yeah, so we name things all the names that we give to features are they're sort of like informal names. There's no sort of like formal recognition of them by like the International Stratigraphic Union or whoever
Yeah,
that makes those decisions. Things have been named after people in the past, but usually it's sort of an in memoriam
right.
thing.
And Mo also wants to know, you have any thoughts of a timeline for the second sample return mission design?
I don't at the moment. So, I mean, I can give you a little bit of the history here, which is that what the animation I showed you was the intended design around sort of mid 2024. And that design, it looks fantastic, but it was becoming clear that it was going to be more expensive than originally proposed and was probably going to push Mars sample return out to maybe like the year 2040.
Hmm.
So the NASA administrator put out a request for proposals to industry and to NASA centers to say like, hey, let's come up with some clever ideas. How can we bring these costs in? How can we shorten this timeline? Uh, that went forward until sort of early 2025. And it looked like we were on a path to both getting the costs reined in and getting the schedule reined in. And then the president's budget request was released, and they canceled the program outright. So we've been kind of into this sort of back and forth between the
Right.
White House and Congress and NASA and what are our priorities and what. So I can't. I
Yeah,
guess I can't really say. I right now I don't know what the next steps will look like.
yeah. And this is a good question. Could microbial life still exist below the surface? All right, and then
It,
I'm going to add to his question and say, what does that mean for sample return?
Yeah, so okay, so it is entirely plausible that if life started on the surface of Mars, and the planet's surface became so inhospitable that that life couldn't survive at the surface anymore, that it may have retreated deep into the subsurface where there's probably still some liquid water in
Yeah,
aquifers. If you go into mines on Earth that are like 5,000 feet below the
yeah,
surface of the planet, you will find little communities of microbes living in the rocks, making a living, very low metabolic rates, but they're there. They're living off of the rocks somehow. So it's possible. And in fact, there are missions that have been proposed to go looking for exactly those things in Martian aquifers. They are sort of on the books, but have not been flown yet. What does that mean for Mars sample return? Do you mean in terms of like, should we be worried? Yeah.
yeah, yeah,
So Mars sample return has the strictest planetary protection protocols of any mission that has ever been flown to this anywhere in the solar system. And it's precisely for that reason. One, if there's something alive in those rocks, we don't want it getting out.
yeah.
And two, if what we really want to know is whether there was something living on Mars, either today or in its past, we don't accidentally want to like sneeze on the rock.
Yep,
And then it's like, oh, we found life, but it came from us.
yep.
So the design of how we keep those samples sterile and prevent anything from getting out of them is really well thought through so that we don't have to worry about Martian microbes, you know, doing bad things.
If we're not already them.
That's right.
Right?
Which
Kayla would like to know if you have any other top candidates for looking for biosignatures in the solar system, like similar like a Europa idea.
Oh yeah. Good question. I guess it's kind of hard not to be excited about Europa, but I know like Enceladus
Hmm.
and Titan also get a lot of attention. Any one of these planets that or moons that has a liquid water, you know,
Yeah.
present somewhere beneath an ice shell, we tend to get pretty excited about these things. I mean, it's a very sort of non-Earth-like environment, so I don't really know how to think about like how would life
Yeah,
emerge and evolve there? But boy, it would be really exciting to go explore these places.
yeah,
Titan's crazy. It has like liquid hydrocarbons running across its
right.
surface at super cold temperatures. I don't know, maybe life can live on, liquid ethane at minus 200 degrees centigrade. I have no idea.
Yeah, that's the one that is the most interesting to me, right? Because the reality is water is it's the solution. It allows the metabolism to work. Why, there's
Yeah.
no reason a hydrocarbon couldn't do that. It'd be bizarre, but yeah.
Yeah. Well, and I think if memory serves, there's a mission coming up to Titan called the Dragonfly mission. I think that's
Mhm.
going to Titan, and it's a helicopter that's going to fly around in the atmosphere of Titan and do all kinds of analyses there, which should be really, really neat.
Um, Changing the subject a little bit, do you have any idea of how long water persisted on Mars? Any relative dates just from counts, crater counts, or anything else?
Yeah, so we think that the time when Mars was sort of most likely to have had, big bodies of water and a thick atmosphere was probably, sometime between, call it, 4.5 billion years ago, shortly after the planet came together, to maybe 3.5 billion years ago. So that sort of first billion years was probably when Mars was at its sort of most Earth-like, and then things really started to shut down from there.
That's always the thing that kills me too. It's just when we see water on Earth, how quickly the evidence for life begins.
Yeah. Yeah, yeah. As soon as we have a
Quickly,
geologic,
relatively speaking, it's still.
no, but it's true. The minute the geologic record kind of
Yeah,
activates on Earth, signs of life start showing up.
yeah,
It happens quick.
yeah. Oh, and we got an answer for us. The Masonic Temple is in the Grand Canyon. Yeah, yeah.
Oh, perfect. Great.
Perfect. Thanks, Russ. Question just in the general, will the slides be presented, be accessible after today? The answer to that is yes. We are recording the presentation and it gets posted onto our YouTube channel, so it'll be available for others. And my colleague Glenda, would you know about the timeline of the Chinese sample return mission for Mars?
I don't know the details of the timing of that, but I do know that this is kind of one of the things that is a big motivator for NASA is, like we have been roving on the surface of Mars since 1997 with the Sojourner rover and
Yeah.
the Pathfinder mission. And NASA has been building towards this Mars sample return mission since that day. So Sojourner was a tech demonstration to say we could drive a vehicle remotely on the surface of Mars. That was followed by the Mars Exploration Rover mission, Spirit and Opportunity, that were there to basically ask the question, was there water on Mars at one time in its past? That was then followed by the Curiosity rover, which was basically there to understand not just whether there was water, but whether the environments that water was in was habitable. Like, could things that we understand from Earth live in it? All of those were successful. And so Perseverance was sent really to make a very sort of scientifically selected collection of samples that we could bring back from to Earth based on all the knowledge that we've been building up over the decades. Um, so so to kind of get back to the competition with China, China may get there before we do. Their sample return mission is sort of simpler, as I understand it. It's basically what we would call a grab and go mission. So they'll land, they'll grab whatever's nearby, and they'll bring it back to Earth. And so it won't have that sort of same scientific selection and understanding of what's going to be in those samples.
Mhm.
Um, but I think we would like to, I think we would like it to be able to say that we were the first ones to bring samples back from Mars and that those samples were the best possible samples for addressing the questions we want to ask about Mars.
Quick question about I would say some geoengineering. President Alex has a question about restarting the magnetosphere.
Oof. Way out. I
Yeah.
would love to know more. I
Right?
don't know if I don't know how you would do that, but it would
Probably, yeah,
be,
probably not, just based on what that would happen and how deep in the structure you would have to be to basically remelt the core.
Yeah.
And
Yeah,
anything we did on the surface probably would mean the planet wouldn't be there anymore.
that's right.
So, Mo, I'm going to save your last question to last, just because it's long, and I'll let you ask it. Did the 1970s Viking mission actually detect life only for us to misinterpret or accidentally destroy samples?
Good question. So I think the general consensus is that there was no life detected in the samples that were analyzed by the Viking landers. However, it is it has become clear as we have continued our exploration of Mars that we didn't know enough about the planet to properly interpret the Viking results. And one of the things that's maybe interesting is that so Viking kind of landed in one place, scooped up soil from where it landed, and put it into an onboard laboratory. And one of the things that I think was concluded was that not only was there no life in the soil, but there wasn't even any like organic matter in the soil. But it turns out Mars's soil is loaded with these salts called perchlorate salts, which
Hmm.
are actually like they're like a dry cleaning compound. They're used in rocket fuel. They're kind of a weird exotic salt. And it turns out when you take those perchlorate salts and organic matter and combust them together in the oven of the instrument that was on board the Viking lander, you get some really weird chemistry going on. And that's probably what we were seeing in the Viking lander results was these reactions taking place in the presence of these perchlorates. So it actually is possible that there's like organic compounds, carbon, hydrogen, nitrogen compounds in Martian soil, but we don't really think it's because it was left there by something alive, at least as far as we can tell.
Yeah. So that's a good question. How do small local dust storms trigger massive planet-wide storms? That's a that's beyond
You
my geology.
Yeah. So Mars does experience these
Uh,
periodic global dust storms. I would recommend that there are experts in Martian
yeah,
atmospheric science. I could hazard a guess, but it would probably be fairly uninformed.
yeah.
Sorry, I wish I knew more about that.
I'm with you on that. I'm going to leave the last question to Mo. Mo, you have a long question, so I'm just going to ask if you unmute and go ahead and ask that question. It's a good question.
Thank you so much. Yeah, I would love that. Thank you very much, Joe, Professor Horowitz. It was an amazing presentation, and I got to learn so much about the biosignatures of Mars, which I actually got to know that was being researched on in Stony Brook for like a month ago, and I think I emailed you back, and you just responded to me like 2 days ago. So
Yeah.
it was a good coincidence. Um, yeah. So my question is like the decadal survey for 2020 didn't talk much about Mars exploration and life detection. Do you think this biosignature candidate is going to affect the decadal survey of 2030 and it will change the mission concepts to Mars? And where would you expect to see the shift? And another part of that is like, it's kind of related, but what kind of research have you seen coming out of this search as of yet? And do you think there's more to explore with your research?
Great. Yeah. Thank you for the excellent questions. So maybe I'll start with the decadal survey. So the most recent decadal survey, which I think was published, 2 years ago now, perhaps, it actually it reaffirmed Mars sample return as the highest priority planetary science mission in the science community. So there's still strong desire there to continue that. I suspect that these results that we're getting back from Perseverance will only sort of further cement that perspective. So we've had two decadal surveys in a row now that have said Mars sample return is the number one flagship mission for the planetary science community. And I imagine that the next decadal will say much the same. And there is a mission concept. in that most recent decadal survey called Emily, MLE, the Mars Life Explorer, which is a mission to look for exactly the things that we were talking about earlier, which is like things that are on alive in the subsurface of Mars today, so extant life. So there's still a strong desire to both understand whether there was ancient life on Mars and whether there's life on Mars today. And I think those priorities will continue into the future. Um, as far as like things that have been happening as a result of us publishing this result last fall, there's a set of additional papers that are coming out from the Perseverance Rover team. They've just started to hit the presses, and they're basically reporting additional findings related to this potential biosignature that in some ways, in many ways, sort of confirm some of our initial findings, which is really exciting. Um, I I'm actually I'm going to be on a field excursion to Scotland this summer to go look at rocks that have these, very similar little sort of leopard spots and poppy seeds in them to try to understand how they formed on Earth. So there's work sort of continuing in that realm as well. And I suspect that this will spur new research. It's going to take a little bit of time for it to kind of get out into the published literature. I'll be at the Astrobiology Science Conference in Wisconsin towards the end of this month. So maybe I'll get to hear a little more at that point, like whether this has triggered new research for folks to go off and do.
Thank you very
Hopefully that answered your
much.
questions. Yeah.
Yes, it
Mhm.
did.
And just to review, Barbara missed the answer to her question. Yes, Barbara, some um, private industries like SpaceX are exploring options in terms of getting involved with the returns. But I'm assuming that's going to be long out, just like it is here on Earth. Joel, this has been fantastic. I really appreciate you taking the time to be with us tonight,
My pleasure.
and everything that you do for your students and our students. We really appreciate it. Hope to have you back again when you have some more results.
Hopefully when I've got that core tube in my hand.
Right? That'd be amazing. I always tell our students that we always forget how much Stony Brook has been involved with planetary studies, right, in terms of the return of the moon rocks and now hopefully Mars rocks. So it's
Yeah,
keep the tradition going.
absolutely. No, it goes all the way back to the Apollo days.
Yeah.
That was what started our department. So
Yep.
yeah, it's a long history there.
Yeah, that's great. Thank you so much. And to all of you joining us, just give us a couple days and this presentation will be posted on our YouTube. So just go to YouTube and search Hamptons Observatory. You'll find it. And again, thank you for joining us, and we hope to see you back at the next presentation.
Great. Thanks so much, Sean. Thanks, everybody.